In this video, we'll be looking at a second example of conjugate addition by enolates, although this is kind of a variation on that theme, but we will be looking at Stork reactions. All right, let's think about the generation of an enolate. So if we have this aldehyde and we treat it with the base is going to grab off one of these protons, and we form this enolate. Now, I always write it using this resonance structure because it's helpful to think about how it reacts. But let's go ahead and consider the other resonance structure, which is actually the predominant resonance contributor. So imagine these electrons move here and these electrons move here. That gives us this. Now, I like to think about it in this form because this carbon acts as the nucleophile and can add to some electrophile. But if we think of it in this form, well, we can still have this carbon acting as the nucleophile. It's just that we have these electrons are going to fold back in to reform the carbonyl, pushing these electrons out towards an electrophile. So let's think about this version, this resonance structure of the enolate, and compare it to this compound, which, if you recall, is an enamine. So we made these by nucleophilic addition of a secondary amine to an aldehyde or ketone. Following the nucleophilic addition, there's also the loss of water, which leads to the formation of the alkene, giving us the enamine. If we compare the structure of the enamine to this resonance structure of the enolate, notice we have the double bond, the double bond. We have the oxygen with a lone pair, actually 3 lone pairs. Here we have the nitrogen with a lone pair. So just as we can imagine these electrons fold in here to reform the carbonyl, pushing these electrons toward an electrophile, well, in the case of an enamine, these electrons can come in here to push away the electrons toward some electrophile. So it is possible to alkylate this position of an enamine. So let's look at a Michael reaction with an enamine. So here we have our enamine, and here we have an alpha beta unsaturated ketone. So this counts as a very mild base nucleophile, and so we're going to focus on the 1,4 addition product. So the nitrogen can help to push these electrons to the 4 position, pushing these electrons here, pushing these electrons here. So that gives us our nitrogen is double bonded to this carbon. This carbon is still connected to the CH3, but now it is connected to this carbon. Single bond, double bond to this carbon, single bond to the oxygen. This is still connected to the CH3, and here we have our H's. And sorry, I forgot an H back here. All right, so this was the enamine, and this was the alpha beta unsaturated ketone. And I also forgot the positive charge on the nitrogen. There we go. That looks better. Now we're going to have a few proton transfers, and these electrons can fold back in here to reform the carbonyl, while these electrons grab a hydrogen from the solvent, for example. And in addition, the solvent could grab off this proton, allowing these electrons to fold in here, pushing these electrons back onto the nitrogen as a lone pair. So that gives us single bond to the carbon, double bond. This is connected to the CH3 and CH2, CH2, C double bond O, CH3. So this was our alpha beta unsaturated ketone, and our enamine has added to it. But notice we end up with an enamine. It's just a bigger enamine. So a Michael reaction or a conjugate addition reaction using an enamine, this is an example of the Stork reaction. But actually, if we take a couple steps back, we're going to see that the Stork reaction is kind of bigger overall. Let's look at that on the next slide. So once again, we are back to this question we had in a previous video about whether the enolate derived from acetone would add 1,2 or 1,4. We're still not going to answer that question because instead we have another way around it. Remember that we can form an enamine by reacting an aldehyde or a ketone with a secondary amine. So I'm going to keep this generic. Let's just react this with NR2, and that is going to give us, we have our CH3, CO minus, CH3, and then our nitrogen, hydrogen, R group, R group. So the nitrogen has a positive charge, the oxygen has a negative charge. We're going to go through a couple of proton transfers. I'm not going to show those explicitly, but that will lead to the OH, CH3, and then here we have our NRR. And keep in mind, because we do not have a hydrogen on the nitrogen, when we lose water, we're going to lose the OH and one of the hydrogens from the adjacent carbon. So what we end up with is a CH2 double bonded to the C, which is connected to the CH3 and connected to the amine. So this is how we generated an enamine. Now, if we react this with the alpha beta unsaturated ketone, let's imagine that these electrons come in here, pushing these electrons here, which pushes these electrons here and these electrons onto the oxygen. So that is going to give us, we've got our CH3 connected to our C, which is connected to our NR2 plus. This carbon is connected to the CH2, which is now connected to the CH2, CH double bond CO minus, CH3. So here is the enamine, and here is the alpha beta unsaturated ketone. We're going to have a couple of proton transfers. These electrons will come back down so that this carbon will grab a proton, and then we can lose a hydrogen from here to reform the double bond to give us a new enamine. So we get this double bonded to this carbon, which is connected to the CH2, CH, now connected to another hydrogen, C double bond O, CH3, and I forgot one hydrogen here, and then here we are connected to the NR2. This was the alpha beta unsaturated ketone, and this was the enamine, and now we have a new enamine. But let's keep in mind, when we talked about nucleophilic addition to aldehydes and ketones, we saw that these reactions were reversible. So An aldehyde or ketone plus a secondary amine will lead to the formation of an enamine. But an enamine plus water and probably acid, that can lead to the reverse, which means the enamine can be reverted back to the ketone. So if we take this new enamine product and we treat it with aqueous acid, then this is going to be converted back to the ketone. So we get the CH3 connected to the C, which is now connected to the oxygen. And then this is back to the CH2, which is connected to this CH2, this CH2, C double bond O, CH3. So notice once again, it's as if we took acetone and we put the enolate onto the alpha beta unsaturated ketone. So the Stork reaction gives us yet another alternative to trying to do conjugate addition directly. This time we are going through an enamine to do the conjugate addition, and then we hydrolyze the enamine to get back the carbonyl. So let's look at another example, but this time we are starting with a target and we want to consider how to prepare this from simpler starting materials. So one option, we could focus on this carbonyl. This would be our alpha position and this would be our beta position. And so we would want this as our alpha beta unsaturated carbonyl compound. But then that would mean that, oh, wait a minute, the beta position is actually part of the ring, right? It's not adjacent to the ring, it's part of the ring. So we would have to actually make two bonds to this. So that doesn't look that good. So that might not work. Instead, what if we focus on this one, and now this is the alpha position, this is the beta position. That would mean that this would be our alpha beta unsaturated ketone, and then this would be our nucleophile. So we want to generate this enolate and carry out conjugate addition. But we are back to the same question, which we dodged. So we're not going to try to make this enolate directly. Instead, we are going to use the Stork approach. So we can convert this to an enamine. I'm going to keep it generic again. We can just use some NR2. And that will give us this enamine. Now, when this enamine reacts with the alpha beta unsaturated ketone, these electrons will come in here, these electrons will go here and here and here, which will give us this CH2 is connected to the C that is double bonded to the NR2 and single bonded, obviously, to the ring. We have our negative over there, we have our positive over here, and then after some proton transfers, we are going to get this. Which is connected to this. And then finally, this enamine can be hydrolyzed to give back the ketone, which means we get this connected to the CH2, which is connected to a carbonyl, which is connected to a benzene, which matches our target. So whenever you have a target, you need to look at it and try to think about, well, can we go the red approach? And if that doesn't work, can we do the blue approach? Trying to think about what you want to happen, what actually would happen, and whether that brings you to your target or whether you need a different approach. So here we've seen a few examples then of the Stork reaction.